Alright, let's get started with today's problems. The first problem of the day is going to be letter combinations of a phone number. So, given a string containing digits from 2 through 9 inclusive, return all possible letter combinations that a number could represent. Return the answer in any order. Okay, so the first thing that I guess this reminds me of is the subsets problem. But with digits instead of pure numbers. So I guess the first thing that comes to mind is that first create a helper function that essentially maps numbers to list string char numbers. So this helper function will give us our list of strings. Then create a secondary function that returns the permutations of n lists. The number of digits is between 0 and 4. Sorry, 0 and 4? Yeah, 0 and 4. And that's length, right? Yeah. Means this algorithm is probably incredibly spicy. And when I say spicy, I mean it is probably O of 2 to the n, if not more. Let's see. Well, we know that there's an edge case here, or a corner case that if digits dot size or length is 0, return empty list, right? I guess the main thing is that let's see. So in subsets, we only need to iterate over a single list. Now we have to iterate over multiple lists. So how does that sort of change what we do? Also, there's no guarantee that the digits that we're given are unique. Right? So it could be very much that we get the same letter or the same digit 4 times in a row, and so we'd have to basically build something like that. But that's fine because we can just have those 4 lists, right? So this is going to be, so assuming that we have n digits, and each digit contains 3 letters, or up to 4. I guess it really doesn't matter, right? Then we would have 3n or 4n size, or 3n or 4n total size in terms of lists alone. So that would be O of n space, I believe, right? Because for each letter in our digit string, we have either a list of 3 or a list of 4 strings, or a list of 4 characters. Then, because for each one we need to iterate over all the digits, and essentially we have up to potentially n for each character, we make up to n choices in terms of what to take, right? Because let me think. So for each character, we have to go through n minus 1 lists, and each list has 3n or has 3 or 4 characters, but we have n minus 1 lists. And so we would have to make a separate copy for each of those n, we'll say 3n, we'll say linear, we'll just say n. So for each of those, we have to make n choices, n copies. So I think perhaps this is O of n to the n time. I'm not too sure about this. I think subsets is one of the areas where my sort of intuition with regards to subsets. I think with regards to subsets and like sort of these exponential choices, I think this is where my big O knowledge really starts to show its holes in the armor, so to speak. So this is something that I would need to sort of think about more. But I think it makes sense that within each because we had to make n minus 1 copies essentially, or n copies of the string of the character at each point, that essentially means that we need to we're going to need n to the n time, which, given this absolutely tiny input limit, I think that makes sense. Because I don't think that even subsets had a limit this small of 4, right? So let's get started with the code. So we know that we'll need a function. We'll say get character list from digit, where digit is a character. When digit is 1, we'll return or 2 will return a list of A, B, and C. 3, D, E, F. 4, G, H, I. 5. I'm just gonna first do this. 6, 7, 8, 9. And in else case, we'll return an empty list. There's probably a better way to do this. J, K, L, M, N, O, P, Q, R, S, T, U, Oh wait, D F G H I J K L M P Q R S T U V, and then finally W X Y Z. So that returns our character list from digit, and this returns a list of character. Then we can say for our digits for each, and we can say val list of candidates equals, it's going to be a list of characters. And for each digit, we are going to say list of candidates dot add. So this should be a mutable list of get character list from digit, adding that as a parameter. Then we can start to consider sort of, okay, so we have that, we have the digit list. So now how do we create, I guess, our list of final items, right? Let's say for this, let's say for example 2 3, which returns A B C and D E F. Well, we want to grab each character individually and combine it with another one from another list. So we take A and we combine it with D. We combine A and E, A and F, then B and D, B and C, or sorry, B and E, and so on and so forth. I guess here it'd be a check to see if the character we really want like a reference to the individual list. So like check to make sure we don't add from our current list. So maybe this would be a for each indexed. And then we use the index as a way of making sure that we don't add from our own. However, there's no way to really know, I guess, now that I'm thinking about it, there's no way to really know, like, I guess natively, like, how do we, let me think about this question a little bit to be a little bit more clear. Make sure that this holds for all candidates. Right, because if we had something like 222, which would be ABC 3 times, we want AAA, and so on. Let me think about this a little bit more. Let's do something that's actually a little bit different. So we sort of C, F, G, H, I, E, D, G. So we take this one, and then we say for each indexed, Let me think. We need the index reference to make sure that we're not going after our own list. We're not combining with our own list. And then we check for each item in there. No, but then each subset also needs to make sure that we're not adding from our own again. Right? So the problem is that we need to make sure we don't get any duplicates for the other lists either. So it's not just if it's not in our list then we're safe. It's that if we've ever added it to our list in this manner, then we need to make sure that we do not add it again. Well, what if we go left to right? So rather than starting with this, so this is like kind of like the subsets thing, right? What if we did A, then B, then C, then for each of them we did AD, AE, F, and then B, D, B, E, B, F, and then C, D, C, E, and C, F. So basically we just go through each one slowly. So we'll have a val list of, I guess we can call them list of sources. And then our list of candidates will be a mutable list of string. And this will start with an empty string. Each one in order, not slowly. I mean, slowly is already implied with this solution speed, but okay. So in that case, we can do list of, oh no, we can't do a list of candidates for each. We have to do list of sources for each. Source list, and then we can do for candidate, or let's see, in list of candidates, because this fires once and I'm fine with that. This checks once, we're fine with that. We don't want to mutate the new values anyways, right? So this is actually fine that the for loop checks once in terms of what candidates to go through. Hmm. Let me think. We still need So at the highest level, we loop through for each list. Then we do for each character in the list. And then we do for each candidate. I think. Could be wrong there. So for each source character, then we do list of candidates, add candidate.append source character. So basically we just want to The problem is that we really have we don't care about the copies. We don't care about the partial products. We only care about the full products. Man, now I'm thinking whether or not a backtracking kind of solution would be better for this. Let's see. If we did a backtracking solution, our condition is that, or our constraint is that our size needs to be equal to the number of the size of the list, right? That's our constraint. I think this might actually work better as a backtracking problem. I think this might work better as a backtracking problem actually. At least after this part. Let me think. If we were to do this as a backtracking problem, what would we need? We would need the current list index. Oh, I just realized that this is because it's in order. This is in order, right? The order of the letters does matter. So in that case, right. Let me think. What if we did continue this iterative map? manner? Well, do go through the list of sources, the list. And for each character in there, we do check that. So we check each character of each list. So go through these. Realistically, at this level, we want to maybe duplicate the items many times as there are characters. So what I mean by that would be, let's see, a list of candidates for each candidate. Or rather, we would want to do like for I in 0 to source list dot size minus 1, or actually dot size. We want to source, we want to do the following. For candidate in list of candidates, list of candidates, add candidate. So duplicate as many times as there are characters within our source list. So basically here we want to duplicate this empty string 3 times. And then rather than adding, we would do just candidate append this new source character. We can say added that. And then at the end, we return our list of candidates. Actually, this should be -1 because that's the number of items in terms of 0 indexing, right? So let's walk through this. For an example like 2, 3. Starting with empty string. So this does, so for each list, well, we're in the first list now. We will duplicate all the items within here from 0 to 2. So 3 times total. So this would create this, 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 and this. And actually instead we can say if list of candidates is empty, otherwise do that. Otherwise we do list of candidates add an empty string. So that would cut it down to this. Then for each character within that list and for each candidate in here. Oh, we don't really want to do for each candidate in list of candidates on that area. Let's see. Because we want to add A here, but the problem is that in this case, right, it'll add A to all of them, then it'll add B to all of them, then it'll add C to all of them, because this is for each character and then for each candidate. So what we really want is that we want to say, okay, you add A, you add B, and you add C. That's what we actually want. So I think we can actually get rid of this outer for loop. And then we have to sort of define source character ourselves. Well, this source character will be equal to, we can say, we can create a var index here starting at 0. And this index will be what we use to actually get the index of the source list, and then we increment it every time. So now we do A, the first one, B for the second one, and then C for the third one. Then for the second iteration, well, we do this each time. So this will result in A, B, C, sort of copied 3 times, right? Because 0, 1, 2. So this adds those. Then we do df for each one. So we do for each candidate in list of candidates. We do d. Oh, but we kind of do want that, don't we? We kind of do want that. We kind of want that, and then E, 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 and F, F, F. We kind of do want that. We can do it in any order, right? Yeah, I'm gonna do some brainstorming on how to do this with the backtracking method, and then I'll be right back, because this is probably gonna take some silence. Okay, so seems like this one went through. So let's actually walk through my backtracking solution now. So this is the main sort of recursive solve function. It's just called at the bottom here pretty much after I initialize the list of sources. We have a partial candidate, which is a string, our source list, a list and a character index, and a solution set, which we add to. So we don't actually return anything, we just add it into this solution set, which we pass in by reference. And then we also have a target length, which will be our constraint essentially for this problem. So first we start off by, well, our first thing is just checking to make sure that we aren't going over the limit. And honestly, I could just put it here. So if list index plus 1 is less than source list.size, then do that. And then if char index plus 1 is less than source list at list index.size, and that way we can maybe cut down on the runtime. But besides the point, so we start by adding our new character from our list and our basically our list and character, our candidate. We add it, and then we see if it's at the same size as we need it to be, the list of digits, possible digits, right? And that's how we know that one, I guess, combination is complete. If that is not the case, then we will go to the next list, right? Because we still have more items to gather. At the end of it, right? So let's go back to this first part. So if it is unfinished, we go to the next list. This is pretty straightforward. So if we create this A, well, this A is not complete. It needs something from the other list. So we increment the list counter, and we go to the next one, and we start at D, right? In either case, whether we have finished a set or we have not finished a set, we will both add the next character after dropping this one. So the idea is that we start at A. A is not finished, we go to D, or the second list, and we add D. So AD is a combination, and we've completed it. Okay. However, we are not done with A. We still have AE and AF that we need to add. So we will intentionally drop the last character, which is the character that we just added to finish the set. And we will go to the next character, which is E. And then we'll drop that after we finish the set and go to the next character, which is F. Once we're done with that, then we finally return. From this first part, because, of course, we will also return, when we return from A after we get a D, AE, and AF, well, we go through the same thing here, right? So our characters in this list is not finished yet. We still have B and C combinations to go through. So we will drop A and go to our next letter, which is B. Well, B is not finished, so we go to the second list, and we go to BD, BE, BF. Same thing, we drop, and we add the next drop, and we add the next drop, and we add the next. And then after that, when we return, we realize, okay, we still need C. We'll drop this, and we'll add the next one. And we go to C, and then CD, CE, CF, and then after we drop this last one, well, now our character index is less than our size, so we've hit the, or is equal to our size, because we've hit the end now, if we add one more over C. So we won't continue, and then we fully return from our procedure. So let's run this another submit again. Adding the if cases speeds it up because we don't run the additional, or we shouldn't run the additional sort of item. But it looks like we have a runtime exception here with 0, 0. Why is that the case? Well, we start off with this empty string. We have 0 and 0 here. We want to add source list at 0 and 0, which does not exist. So we'll say that if... Didn't we add a... No, we did not add the edge case. Okay, so if list of... or digits dot size... No, length is equal to 0, we will simply return an empty list. Let's make sure that it works for first 2, 3, 4, and then our blank string. But in any other situation, index should work, right? Because there should always be something at 0, 0. And yep, this is a little bit more on the average side of speed. And so this is where I'm going to leave it. And in any case, I hope you learned something, and I will see you for the next problem.